Okay, so welcome to part 2 of section 4.8. We are going to continue to use tangent lines to approximate. Here I want to do an approximation of the cube root of 26. Okay, so remember the idea behind tangent lines as an approximating tool is you're going to have a function that plays well with some numbers, doesn't play with other numbers. You're going to make a tangent line in one of the nice numbers and use it to approximate the ugly numbers that are close to the nice number. So if you think about what we're doing here, since my job is to take a cube root, I'm working with the function f of x is equal to the cube root of x. And if we make a quick just sketch of this, we're looking at something that comes in like this, right? Right. Now out here somewhere is going to be the value that I want to know when x is 26. What is the cube root of 26? Now I can't know that because I don't know how to take the cube root of a number that is not a perfect cube. So what I'm going to do is I'm going to look somewhere close to 26 and try to find a number that is nice, like maybe 27. And then I'm going to go up to the curve at 27. I'm going to draw in a tangent line at 27, and I'm going to say, the tangent line is close enough to the curve. So let's use the tangent line to approximate the cube root of 26, and it should be a good approximation, right? So, in terms of the language of linear approximations, f of x is approximately f of c plus f prime of c times x minus c, where this c that is here and here and here is our nice number. That's going to be the 27 that we're going to use. Okay? So let's use that 27 here, here, and here. Right. Now, just like last time, though, I need to know a couple of pieces to put it in here. So I'm going to go over here on the right and start finding those things. Let's see. What are the things I need to know? What are the things I need to know? I need to know, first off, what is f of 27? Right? Well, f of 27 is the cube root of 27, which is 3. Okay? I need to know f prime of 27. Well, before I can take the cube root, the value of the derivative there, I need the derivative. So what is f prime of x? Well, f prime of x is 1 over 3 times the cube root of x squared. Again, this is one like the square root function where I've done it so many times that I know the derivative. Okay? Rewrite as a fractional exponent. 1/3, take the derivative, it's 1/3 times x to the negative 2/3. Negative 2/3 means puts it downstairs, square it, and take the cube root. Okay? So then f prime of 27 is going to be 1 divided by 3 times the cube root of 27 squared. Okay? So that's 1 over 3 times 3 squared. Right? Remember, when you take the cube root of something squared, you can take the cube root and then square it, or you can square it and then take the cube root. Either way, I'm going to choose to take the cube root then square. And so that gives me 1 over 27. So then putting all of this where it belongs down there, I get the statement that f of x can be approximated by f of c, which is 3, plus the value of the derivative at 27, which is 1/27, times x minus 27. And now I'm going to use it to approximate the cube root of 26. So f of, whoa, that got ugly. F of 26, which is our cube root of 26, is approximately 3 plus 1 over 27 times 26 minus 27, right? Which is approximately 3 minus 1/27. Let's see, 27 times 3 is 60, 70, 81, so this is 80 over 27. So I get that the cube root of 26 is approximately 80 divided by 27. Now, I'm going to do the same thing I did last time. I'm just going to use my calculator to see how close we got. Let's see, the calculator, 26 raised to the 1/3. That's the cube root. It thinks it's 2.962496, blah, 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 blah. We got 80 over 27, which gives us 2.962. Ooh, so we have accuracy about to hundredths place. If we round at thousandths place, we wouldn't be the same. 2.962, 2.963. So we're pretty good. We're reasonably accurate. I'm liking what I'm seeing. I'm not unhappy with it. So I'm happy. I'm feeling pretty good. I can do a linear approximation. So essentially, I'm drawing a tangent line. Now, what are the things we need to figure out to make this work, though? Right? Well, I have to be able to look at what I'm being asked and figure out what the function is that's hiding behind that. I also have to be able to figure out what's the nice number, the 27 that we used everywhere, that is close to the ugly number, the nice number that plays well with the function. So for example, what's the number we're supposed to use here? What's the function we're supposed to use here? I'm supposed to figure out what is 1.999 raised to the 5th. Now, if I had nothing else to do all day, if I just wanted to sit around and do nothing, I could easily just take that number and multiply by itself 5 times. It wouldn't be pretty, it wouldn't be fun, it wouldn't be quick, but I could do it. But I could also do approximation. So what do I need? Well, I need the function, and I need the value c. So the function we're working with here is raising to the 5th, and the number that's close to 1.999 that plays well is going to be 2, because I can take 2 to the 5th and do that pretty easy. What is that? 2 times 2 is 4, 8, 16, 32, and I'm done. Right? Now, tangent line approximations say that f of x can always be approximated by f of c plus f prime of c times x minus c. Now, I know f of x, I know c, I don't know f prime, so I'm going to go ahead and figure that one out real quick. F prime of x, 5x to the 4th. Okay? And so now I can say that f of 1.999, which is going to be 1.999 to the 5th, is approximately, let's see, f of c is 2 to the 5th, so that's going to be 32, plus the derivative, so that's going to be f prime of c, so 2 to the 4th is 16 times 5. 5 times 16 is what, 80? Times x minus c, so that's going to be, what is that? 1.999 minus 2. So that's going to be approximately 32 plus 80 times 1.999 is 1999 tenths hundredths over 1,000 minus 2, so that's 2,000 over 1,000. So that's going to be 32 plus 80 times negative 1 over 1,000. That's 32 minus 8 over 100. So that's 31.92. 32 minus 8 hundredths, 31.92. So 1.999 raised to the 5th power, my approximation is 31.92. 1.999 raised to the 5th, 31.9200. We got 31.92. I feel pretty good about this. I think this is amazing that this works as well as it does. I mean, the geometry of it says it should, and then the reality is it does. Now, you might be thinking, wow, why don't we just do this all the time? Someone did. That's what a calculator is. it's doing an approximation technique very similar to this. Right? The challenge is, the difficulty is figuring out what that nice number is. Now, we've had some simple examples so far. Remember, simple doesn't mean easy. Big picture, 1.9992. 26 cube root 27. We should be able to see this. 3.98 and 4.05. We should be able to see that 4 is the number that's close to it that works well. But what if things get a little bit more challenging? What if we have something like this? Right? I know what my function is. My function is f of x is equal to the sine of x. I know my ugly number is 1.5, but what's a nice number that's close to 1.5 that plays well with sine? Well, I want to say this. Pi over 2. Because pi is about 3, and 3 divided by 2 is about 1.5, so I think pi over 2 would work well with this. So I've got my nice number. I've got my function. What am I missing? Well, tangent line approximations say that f of x is approximated by f of c plus f prime of c times x minus c. So I need f prime. So if f of x is sine, what's f prime? Well, derivative of sine is cosine. And then putting it all together, what do we have? We have that f of 1.5, which is going to be the sine of 1.5, is, ooh, that didn't come out really nice at all, is going to be approximated by, let's see, f of c is going to be the sine of pi over 2 plus the cosine of pi over 2 times 1.5 minus pi over 2. So then the sine of 1.5 is approximately, let's see, what's the sine of pi over 2? The sine of pi over, so since the sine of pi over 2 is 1, plus the cosine is 0 times 1.5 minus pi over 2, we get the sine of 1.5 is approximately 1. So let's see what the good old people at TI think. Sine 1.5, 0.997, we got 1. We're off by, what, 3/10 thousandths? I can live with that. All right, so this brings us to the end of the tangent line approximation part of section 4.8. The next video will talk about differentials and the idea of using differentials, which is a tangent line thing, but in a different way. So I'll see you all back here for part 2 or part 3.